Good morning, physics class. So we got some momentum work here. We're going to look at some example questions from your practice sheet. There's two practice sheets. There's it says momentum and impulse practice sheet, and then there's momentum and impulse practice number 2. We're going to start off with our momentum and practice sheet, just the first one, the one that has the answer key that's laid out how it usually is. We're going to do questions 2, 5, and 7. Honestly, I think we should be able to kind of bang these out pretty quick. They're not too hard to understand. We have our simple formulas this week, just introducing the topic of momentum. So momentum equals mass times velocity, impulse equals force multiplied by time, always net force, and then remembering that impulse is the change of momentum. So I think we should be able to do pretty good on these. So let's get right into it. This one, let's see what pops up. All right, so it says a 5 kilogram object has a momentum of 25 kilograms meters per second, okay? That is our SI unit for momentum, kilogram meters per second. It's probably the most annoying one that you'll find just because it's so long. There's no substitution to make it smaller with just one letter, kilograms meters per second. So that's what it is. So momentum equals 25 kilograms meters per second. It says what is the velocity? Simply just take our little formula. Velocity would end up being momentum over mass. So 25 over 5, and our velocity equals 5 meters per second. Okay, just want to do that question, really just get the SI units in there. Simple question. Let's go to question 5. Question 5. All right, sometimes, and I don't like to try and sneak things in. I hate questions that are there to try and trip you up, and I'm not trying to put these kind of questions there to trip you up. But for those of you that are going into possibly next level physics or sciences, or going to be using this policy stuff somewhere else next year at all, there's a lot of these questions and a lot of just understanding what the question means. So it says a 6.6 Newton object. What the heck does Newton means? Well, if you think of what we use Newton's for, it's force. So it means like the force of gravity on this object is 6.6. Okay, so force gravity on this object is 6.6. Is traveling at a velocity of 3 meters per second. Okay, what is the object momentum? So I need to find momentum. Okay, basically I want mass, right? Like I want this to turn into a mass. Well, again, to get force of gravity, you have to go mass times gravity. So if you want to go backwards, if you're ever given a force of an object, like the Newtons, again, that is the force gravity on it. And so you're just going to take this, divide it by 9.8, and you'll get the mass. So this one, 6.6, turns into 0.67 kilograms. Okay, now nicely we can take this, our momentum looks at 0.67 times 3, and we get a momentum of 2 kilogram meters per second. It is going, I believe, north. Okay, we do need direction for momentum. It's not going to seem like it's that important this week at all, because I'm not doing a whole lot of directional stuff, and I'm not doing a whole lot of collisions or a lot of explosions, that kind of stuff. And so this week is going to kind of seem tedious to actually put in a direction. But come next week, I'm going to have something traveling like northeast and something traveling west, and then they collide, and then there's a conservation momentum. And those directions are going to become important. Kind of just like when we had our, breaking our vectors apart and understanding some of that stuff. This is going to be kind of similar, okay? So I'm going to keep adding in our direction for now. All right, and question 7. Cool, question 7 again. We've talked about how dynamics and kinematics and how now even energy is going to consistently just kind of keep weaving its way back into even any of these questions. And this is a question that is going to happen for that. It says a mass, 5 kilograms, is dropped from a height of 2.5 meters above the floor. What is the object's momentum after 0.25 seconds? So 0.025 seconds, and a height of 2.5 meters. Okay, well, that's our height. We can kind of try and figure this out. There's a few ways that we can kind of try and figure this out. All right, you could use a full kinematics in the sense of if you're dropping something, you're going to have a VI, you know the acceleration, And so you could kind of figure out that, because what do we need? We need the actual like velocity. We need velocity final after 0.25 seconds. Okay, that's what we need to know. All right, so this thing drops for 0.25 seconds. What is the actual velocity final now? And again, you could use your kinematics. You could use energy. I'll kind of maybe show it both ways. Let's go with our kinematics way. Kinematics. And so I have a VI of 0. I have an acceleration of 9.8. Okay, I have a time of 0.25, and I need to find a VF. All right, so not too bad. I could use this formula. Okay, our acceleration equals VF minus VI over T. So there's one way, and so let's find this answer right now. In this sense, I could go like, VI is 0 nicely. So basically, this ends up being like I need to find my VF. So it's going to end up being 9.8 equals VF over 0.25. So multiply by 0.25, multiply by 0.25, and VF becomes 2.45 meters per second. Okay, so there's the kinematics way. All right, let's do our energy way. All right, energy is a little tougher because of that time in there, but we can try and figure this out in the sense of what's our potential energy. All right, well, potential energy is mgh. So we have a mass of, where's my calculator? Oh, I missed my calculator. There it is. All right, mass of 5 times 9.8 times, what's the height? 2.5? 2.5. Okay, we have potential energy. That is 12.25. Oh wait, we need to kind of get that into my kinetic energy. The problem is I don't exactly know how far down it's going yet. I can't figure out a distance. So I might have to use some kind of kinematics to try and figure out how far it went down. Because again, I would need that change in energy to actually figure out, like, again, what's my new height. And so if I wanted to kind of go this way, I would need to find, like, where is my new height? And so I'd have to calculate for my distance traveled here. And then I'd have to put it back into here and find what my change in potential energy is. That'll give me my kinetic energy. Okay? So the energy way, this one is not exactly doing great here. It could work out better in a different scenario, but it takes a little more steps this way. Kinematics is a faster way. Again, if you want to do the energy way, you have your potential energy here. You just have to find how far distance-wise it went down after 0.25 seconds. And then you have that new height there, and that change in energy would allow you to find our kinetic energy and our velocity. Okay? So for sure would absolutely still work. Kinematics in this one works out. Okay, so now that I have that 2.45 over there, I can pretty much easily figure out what's the momentum now. Because I have mass, so momentum equals 5 times 2.45, and momentum ends up being 12.25 kilograms meters per second. I can't totally give a direction here. I could say down because it's being dropped. So in the sense of when things are going up and down, we usually don't put an actual direction on it. You could say down here though, but we'll leave it as it is. Okay, so there's the first kind of 3 questions, how I go through them. Again, knowing that those kinematics, those dynamics are going to kind of keep making their way into these questions. We have 2 more videos, again, basically going back and forth off these actual practice sheets to kind of help us out. All right, class, thanks so much. I'll talk to you soon.